Hello everybody and welcome to my 13th video. This is on ternary counter and divider circuits. I'll be demonstrating how you wire up the ternary D-Type flip-flop, T-Type flip-flop and JK flip-flop to make counter and divider circuits. So first we'll start with the unary operators. Here we have the unary operators from a ternary algebra, a ternary post algebra with counter maps, and here we have the unary operators from a ternary algebra with counter maps, which is the third and fourth videos I think in my ternary series. And here we have two unary operators here, which I'll explain later. So first we have the successor function, which is a plus 1 modulo 3, which is in response to 0, 1, 2 we get 1, 2, 0. This is the predecessor function, which is a plus 2 modulo 3. So in response to 0, 1, 2 you get 2, 0, 1. This is A1, which is a 1 if A equals 0 and 0 otherwise. And this is A2, which is 2 if A is 0 and a 0 otherwise. So these unary operators, A0 is 0 is a 2 if A equals 0 and 1 otherwise. A11 is a 2 if A is a 1 and 0 otherwise. A22 is a 2 if A is a 2 and 0 otherwise. A01 is a 2 if A equals 0 and 1 and 0 otherwise. And A12 is a 2 if A equals 1 and 2 and a 0 otherwise. So here we have the diametrical inverter function, which basically call it A bar for want of a better word, but it reverses the order of the A in the truth table. So in response to 0, 1, 2 we have 2, 1, 0, and this out function, which I've called Z, preserves A and swaps the 2 and the 1 around in the truth table. So these are the flip-flop symbols. This is the D-Type flip-flop, the T-Type flip-flop and the JK flip-flop. These are ternary flip-flops, and this is the symbol for D, T and JK. I've used conventional symbols, as in with the binary flip-flops, because I couldn't decide what to use, but these are ternary flip-flops. So here for the D-Type flip-flop we have a D, a clock, a set, a reset and a Q and a Q bar. For the T-Type flip-flop we have a T input, a clock, a set, a reset, a Q and a Q bar. For a JK flip-flop we have a J input, a K input, a clock, a set, a reset, a Q and a Q bar. Q is the output, and Q and Q bar are the outputs, and then you have the D input, T input and J and K inputs. You can wire a JK flip-flop to act like a D flip-flop by adding a Q bar function to the K input of the JK flip-flop, which performs this function Q bar, and you can wire a JK as a T flip-flop by adding this function to the K input, which is this function here Z, which I've called Z. So in response to 0, 1, 2 you get 0, 2, 1. Now the set and reset functions on the flip-flops are active low, and they are activated by a ternary logic 0 only. They won't be activated by a ternary logic 1 or a ternary logic 2, and the clock inputs are a negative edge triggered from a ternary logic 1 to a ternary logic 0. So a negative edge of a ternary logic 2 to a ternary logic 1 won't clock the flip-flop, and a positive edge of any description won't clock the flip-flop either. Right. Going to go for a divide by 3 counter here. So this is the clock from a 0 to a 2, and this is Q here. This is the reset. So Q and reset. So on the negative edge of a ternary logic 1 to a ternary logic 0, the output Q advances 1. So it goes from 0 to 1 to 2 back to 0 and repeats. And this reset here, which momentarily goes to a 0 and then for the remainder goes to a 2, resets the Q output to 0. So this is circuit A with a D flip-flop with a successor function from the Q to the D. This is circuit B with a T flip-flop with the input T set to 1, and this is the JK circuit with J set to 1 and K set to 2. Right, this is a divide by 2 counter. Here we have the clock again, which alternates between a 0 and a 2. The Q, which alternates between a 0 and a 2. On the negative edge, it changes state on the negative edge of each flip-flop of the clock. So Q goes from a 0 to a 2, so 0 to 2. The reset momentarily sets the reset to 0, which sets Q to 0. And circuit A, we have a D flip-flop with D wide to Q bar. For a T flip-flop, we have Q wide to T with a predecessor function. And for a JK flip-flop, both J and K are set to 2. Here we have a divide by 6 counter, which is basically a divided by 3 counter followed by a divide by 2 counter. So here for every 3 clock pulses we get 1 clock pulse from QA. Every 6 clock pulses of the clock we get 1 clock pulse of QB. So this is basically a divide by 3 counter followed by a divide by 2 counter. We have a momentary reset to set QA and QB to 0. Here we have the circuit diagrams for the divide by 6 counter. Here we have the divide by 3 counter using D flip-flops and divide by 2 counter with D flip-flops. Common reset and the Q of QA feeding the clock of QB. Circuit B, we're using T flip-flops. This is divide by 3 stage and divide by 2 stage with this predecessor function from Q to T for the divide by 2 and divide by 3 T set to 1. And for circuit C we have JK flip-flops. The divide by 3 section is J is a 1 and K is a 2, and divide by 2 circuit stage is J equals 2 and K equals 2. All circuits have a common reset, and in each case the clock of the divide by 2 circuit is fed by the Q output of the divide by 3 circuit. Here we have a 2-trip Synchronous Up Counter. This is the timing diagram and this is the circuit diagram. We're going to implement it using T flip-flops. Here we have the clock, and both of them are divide by 3 counters. So the QA, which is a set to a 1, counts up 0, 1, 2, 0, 1, 2 in response to the negative edge of the clock. And then every 3rd clock pulse, the QA provides a negative edge clock pulse from Ternary logic 1 to Ternary logic 0, which clocks QB, the next stage, so that counts up. So that's an 2-trit Synchronous Up Counter. Trit standing for ternary digits. And we have a momentary reset here which sets QA and QB to 0, which is there. Here we have a 2-trit down counter. This is the timing diagram and this is the circuit diagram. And basically the circuit is the same as the up counter, except the outputs are taken from Q bar for both flip-flops. So QA counts up as before, not QA counts down, and on the negative edge of QA here, QB, which feeds from QA, counts down. So, and then we'll have a common reset, which resets QA and QB to 0, so not QA bar and QB bar will be 2s. So that's the 2-trit synchronous down counter. So here we have a 2-trit synchronous up counter. This is the present state table for the counter. Here you have the present state QA and QB, the next state QA and QB, and we're going to implement it with the T flip-flop. So I'm going to use the function QA1, which is a 1 when QA equals 0 and a 0 otherwise. So basically, if QA and QB are the same, then you're not adding anything to the Q, to the flip-flop, so TB is a 0, 0 there. But here for QB, you're adding 1 to the, from the present state to the next state, so TB is a 1. For TA, for QA, the next state is always 1 more than the present state because it's counting up, so TA is always 1. Right. So yeah, so when it should be not QA2 or a 1. So when A is a 2, QA is a 0, and sorry, TB is a 1 there. I'll show you in the next set. So here we have the timing diagram. So when QA counts up, not QA counts down, QA bar counts down, and TB, which is the 1 function, is a 1 when not QA is a 0 and a 0 otherwise, and QB counts up when TB is a 1 and the clock is applied. So that counts up 1, 2, 0, 0, 1 to 2 to 0. And we have a momentary startup reset, which is a 0 and goes to a 2. So here I have the 2-trit synchronous up counter circuit diagram. Basically you have the 1 function here, x1, which is a 1 when Q bar is a 0 and a 0 otherwise. So this first stage is an up counter which sets T to 1, and then on the clock pulse when T is a 1 this clock's up. For the 3-trit synchronous up counter, I haven't done the state table or the timing diagram, I've just done the circuit diagram. But when QA is a 2 and QB is a 2, not QA, Q bar A and Q bar B will be 0s. That feeds into a maximum function, will give a 0 when both the inputs are 0, which makes x1 a 1 when the outputs are 0, which feeds into T, which advances the QC flip-flop by 1. So that's how it counts up. Here we have a 2-trit synchronous down counter. Here we're starting at 2, 2 and ending at 0, 0, so counting down. So for QA and QA of the present state and QA of the next state, it's always 1 less. So that TA, which is the T flip-flop, is always a 2. For QB, we've got 2s there, QB and QB next state are 0. T input is 0 because they're both the same, and here is 1 less, so TB is a 2. And I'm going to use the QA2 function here, which is a 2 when Q equals 0 and 0 otherwise. So we're taking the output of this function from QA here, which is a 2 when Q equals 0 and a 0 otherwise. We have the secret synchronous down counter timing diagram. So QA counts down, TB is a 2 when Q equals a 0 and a 0 otherwise, and QB counts down when TB is a 2, and on the negative edge of the clock pulse it counts down. So it goes from 2 to 1 to 0 back to 2. And we have a set function here which sets QA and QB to 2. Here you have the circuit diagram for the 2 synchronous down counter. Here T is set to a 2 here, counting down for this first flip-flop, and then we have the X2 function, which is a 2 when QA is a 0, which counts down the flip-flop B. So from 0 to from a 2 to a 1 to a 0 as the T input is a 2 or a 0. Then you have the reset, which is set to 2. The set input is set to the set inputs of the flip-flops, and we have a common clock. I've done a circuit diagram for the 3-trit synchronous down counter, which basically, when QA and QB are zeros, they're fed back to the maximum input, maximum function, which is a 0 when both inputs are 0, which generates a 2 from the X2 function, which is fed into the T, so that counts down when X2 is a 2 and a 0 otherwise. So here we have the resets at 2, common clock, and inputs fed from the Q of the previous flip-flops. Here we have a 3-trit ring counter. This is the QA, QB and QC here. Basically you set up, I've arranged for a setup which is a momentary logic 0, which sets QA to 2, QB to 0 and QC to 0, which is this setup here. And the feedback goes from QC to the D input of QA. So we have a 2 0 0, then on the clock pulse, which is common to both, common to all the flip-flops, the 2 goes to QB, then on the next clock pulse the 2 goes to QC, and then it's fed back on the next clock pulse to back to 2A to the start. So this is the 3-trit ring counter implemented with D flip-flops, and in each case the set of QB flip-flop B and flip-flop C is set to 2s, and the reset of flip-flop A is set to 2, so it's inactive. Here we have a 3-trit twisted ring counter. Here we have outputs QA, QB and QC here from the flip-flops, and the only difference between this flip-flop and the ring counter is that the feedback has a successor function in between the QC and the D input of flip-flop A. So the momentary reset sets everything to 0, QA, QB and QC is 0. A common clock So this is the feedback, which is a 1 when QC is 0. So it's always 1. The feedback is always 1 more than QC, modulo 3. So it basically shifts right, so the feedback goes to 1 and the 0, 0 shift, 1, 1, 0, 1 there, 1, 1, 2 there, 2 there, shifts, 2 there, shifts, 0 there, shifts, 0 there, shifts, until you get back to here again. It basically shifts right, all digits shift right. So this is the decode, which I haven't shown on the diagram. Basically, the decode is a 2 for one of these lines of the truth table only and a 0 otherwise. So I'm using the 2 function to do this and the maximum function. So when QA and QC are zeros, the maximum function is a 0, and that makes the 2 function a 2 and a 0 for everywhere else. So I think you only need a maximum of 2 inputs to the maximum function to decode a twisted ring counter for any number of trits. So common clock, reset, and QB feeding QA and QB feeding an input of QC, input of flip-flop C. Right. Here we have an asynchronous modulo 10 counter. This is the truth table and the circuit diagram. Basically, the clear, which is this output here feeding the reset of the flip-flops, the 2 for every state except 10, 1 plus 1, yeah, 10, 9 plus 1 is 10. So it's from 0 to 9 and then resets at 10. So we have QA, QB and QC here. You're implementing it using T flip-flops, so they're all counting up with T input set to 1. And I'm using the successor function here to the inputs of the maximum function, which is in response to 0, 1, 2, it goes 2, 0, 1. So you can see when QC is a 1 and QA is a 1, that goes to a 0 of the predecessor functions, and that makes this line all 0 inputs to the maximum function, which gives a 0 out, which resets the function, resets the flip-flops. So you count from 0 to 9 and then 10 it resets. So we have it's asynchronous, so each Q output from a previous flip-flop feeds the clock to the next stage, and so on. Okay. Here we have a Synchronous Modulo 7 counter. I'm going to introduce this, well, I'm going to implement it using JK flip-flops, Ternary JK flip-flops. So this is the excitation table for a JK flip-flop. QN is the present state and QN plus 1 is next state. And this for QN 0, 0 you get as J is a 0, 0 and X is a don't care state. The X can be any value 0, 1 or 2. And for this line I've got X and a J plus 2. So J can assume any value, but K has to assume the value J plus 2. And here, J can assume any value 0, 1, 2, but K has to assume the same value J. And here, J can assume any value 0, 1, 2, but K has to assume the value J plus 1, modulo 3, of course. So here, I've filled in the gaps here, or the numbers. So I'm using 0 and 2 for J and K for this one, 0, 0 for J for that one, and 1 and 2 for X and J plus 1. The reason I did that is because these lines of the truth table don't appear in the table for the present state and the next state. So J and K can be only two valued, which simplifies the counter maps or the design for the J and K inputs of the flip-flops. So for example, if QB and QBN plus 1 is a 0 to a 0, J and K, JB and KB are 0 and X. And so for example, QAN and QAN plus 1 is a 2 to a 0, 2 to the 0 is an X plus a 2, and we have an X plus a 2 here. So that's basically, you look at the present state and the next state, which is that's the present state, that's the next state. Look at the two values of Q and Qn plus 1 and determine the value of J and K for the two flip-flops respectively. Okay, now we'll go straight to the counter maps. This is J, K, JB and KB. These are the inputs J and K to the flip-flops QA and QB. And here I've looped this group of 6 ones here, which is one minimum QB01 or 0 Q, yeah, QB01. And here for K, I've looped the whole counter map, so K equals 2. For input JB, I've looped this group of 3 here and used that X as a 1 and these X's are zeros. So that's 1 min QA22. And for this input KB, I've looped this loop of 3 here and this loop of 3 here. So KB equals QA22 or maximum of QA22 max to QB22. So that's QA1, the inputs are 2, and QB when the inputs are 2 there. So for the circuit diagram, here I have the input to JB and KB. These are the maximum function for KB. That's minimum 1 and X22 for JB, and KA was a 2 and J was 1 minimum of X01, so that's a J. Right, so, and then you have a common clock. I haven't included the set and the reset. I'll just go back and point out when QB and QA are a 2 and a 0, that goes back to 0, 0, which is here, and that resets the count again. So the remainder of the states, 2, 1 and 2, 2, should go to 0, 0, which is this state here. So that was the circuit diagram. And lastly, we have the startup reset circuit, which is when this capacitor is discharged from on switch on, it charges the capacitor, which the Schmitt triggers will be a 0, and then when capacitor charges to a logic 1, these Schmitt triggers will go from a 0 volts to 5 volts. So that momentarily produces your set or reset signal, which was in the timing diagrams. And so C charges through the CR circuit through the power supply. And if the circuit was switched off, the diode discharges the resistor, so you get an instantaneous discharge. So if you momentarily switch on and switch off, the set and reset will still work. Okay, I think that concludes the presentation. I hope you enjoyed it. Thanks for watching. Bye.